Okay, well, we're going to return back to Almeria after the two presentations in the Netherlands. The title of my presentation is Fertigation Management in Almeria. Now, it might seem a little bit strange having an Australian talking about fertigation management in Almeria. We did have a plan for a Spanish person to do it, but that fell through, so I'm here as plan B, okay? Okay, this is the sea of plastic. This is taken probably to the west of here, okay? When we first started trying to characterize this agricultural system, we started talking to people, and they would tell us it's very difficult to characterize farming in Almeria because each farmer is different, each greenhouse is different. But although there is variation, it is an agricultural system with its own characteristics and its own tendencies. And in this presentation, we'll look at some of those characteristics and tendencies in the context of fertigation and irrigation. And the information that will be presented has come from various sources, from various surveys, from the Cajamarca, from IFAPA, from our own work, from practical manuals, discussions with technical advisors, researchers, etc. Okay, as we've seen from the presentation of Juanjo, there's essentially two main groups of systems, fertigation systems used in Almeria. There's the simple fertigation tank, which is known locally as the abonadora. In this system, fertilizer is manually added, and then it's manually operated. The irrigation water is diverted through the tank to carry the water, well, the nutrients in the fertilizer to the irrigation system. In this system, the nutrients are applied on a rate basis. That's the number of kilograms per hectare is known, or kilograms per metre, or 1,000 metres. This is a traditional agronomic approach where management is based on rates. And the amounts to be added can be based on crop nutrient uptake curves, on soil tests, etc. The other type of system that's used here and is increasingly being used in Almeria are the multi-tank systems with a controller, with a programmer. These are computer-operated systems. Generally, there's 2 to 5 tanks of concentrated fertilizer solution, plus an additional tank for acid. There's 1 to 2 fertilizers normally per tank. The tanks are prepared every so many days, commonly once a week. In our experimental greenhouse, we have large tanks in a small greenhouse. The solutions might last a month. In this system, the programmer automatically applies programmed irrigations and nutrient solutions. Approximately 50% of the soil-grown crops at the moment have this type of system, and the proportion is rapidly increasing. But with this system, as in substrate systems, the nutrients are applied on a concentration basis. And a consequence of this is that growers don't readily know how many nutrients they've applied, what are the quantities that they've applied. So they have to make some calculations. This actually didn't come out the way it was meant to come out. Okay, sorry, no, okay, sorry. This is a comment, it's okay. Okay, now when applying concentrations with these systems, it's difficult to adjust the applied concentration to the results of soil tests. It's difficult to consider nutrient uptake curves. It's also difficult to use accepted agronomic procedures that are used to optimize nutrient efficiency. So while these systems have many practical advantages, it is a challenge to be able to optimize fertilizer use efficiency with these systems. All of the greenhouse areas in Almeria have been declared nitrate vulnerable zones, which means that the growers are obliged, well, eventually, to implement improved management practices. Part of the improved management practices are that there are limits on the maximum amount of nitrogen applied to a single crop. In Andalusia, this is the way in which the limits are determined. It's based on yield, and then there's so many kilograms of nitrogen can be applied for each tonne of yield, okay? And the amounts vary for different species. But if you know to do this, you've really got to know how much you're applying. And with concentration-based fertigation systems, it's difficult to know how much you're applying. Now, despite the challenges that are associated with optimizing fertilizer applications with these high-tech systems, they do have enormous potential. If we look here at what happens in a traditional nitrogen management system using an open field crop, normally at the beginning of the crop, there's a pre-plant fertilizer application. And later on during the crop, there might be 1 or 2 applications. And we can see there are big increases in the amount of mineralite in the soil over time, which we can see here. With fertigation systems, there are many frequent applications of nitrogen, small applications of nitrogen over time. So in effect, we have the possibility of spoon-feeding nitrogen to the crops. As we've seen, there are technical issues in terms of really accurately dosing the amounts we apply. But once we can do that and we have the tools to know how much to apply and to make corrections on that, we have the capacity for a really sophisticated nutrient delivery system. Okay, now we're going to move on to the traditional management criteria in Almeria for irrigation and fertilization to consider together. Generally, it's based on experience, on fixed schedules and standard recipes. We've called this collective experience. It's the experience of the growers, of the technical advisors, and it's all gone together and that there are adaptations, etc. But people know what works from their experience. They know how to produce crops, economically productive crops. Basically, the farmers know what works and what consistently gives profitable production. Of course, there are variations between farmers. Now, regarding irrigation, generally irrigation is based on fixed schedules. For example, it might be 30 minutes every 3 days a week, 3 times a week, and then when the weather gets warmer, the plant is bigger, 20 minutes every day. These schedules are flexible. The adjustments are made in response to weather conditions, crop growth, the appearance of the crop, etc., etc. As we saw with the Aurora, there is a use of tensiometers. Approximately 10 to 15% are using tensiometers, which mightn't seem much. But when I spoke to the main distributor of aerometer tensiometers in Spain, he said that Almeria was by far the single largest market. So for him, there's a tremendous use of tensiometers in Almeria. Okay, regarding fertilizer management, traditional fertilizer management in Almeria, in particular the simple fertilizer tanks. Generally, the fertilizer addition is based on a standard fertilizer plan, which is a fixed schedule. An example will be given in the next slide. Again, adjustments are made to the program depending on crop appearance, weather, etc. The amount of nitrogen can be reduced when the crop has too much vegetative growth. More potassium may be added to promote fruit growth. These observations apply also to the multi-tank systems in terms of the adjustments that are made to crops, to the fertilizer recipes. Now, this is a recipe that I got from a very good chapter by Paco Cadenas, Jesus Gonzalez, and Fernandez, which is Protected Production of Tomato in the book by Paco Camacho. This is a recipe that I understand came from Jesus Gonzalez. This is for a simple fertilizer tank. The first week after transplanting, no fertilizer is applied. In the second week, ammonium phosphate. In the third and fourth weeks, potassium nitrate and ammonium phosphate. From week 4 to the fruit set of the second truss, that's the ramillete, there's an alternation from one irrigation to another. In one irrigation, ammonium phosphate, potassium nitrate, ammonium nitrate, and in the second irrigation, some nitric acid, and calcium nitrate. And then basically this recipe, this approach of alternating the two fertilizer mixes, is followed for the rest of the crop, with the amounts increasing as the crop gets bigger. Now moving on to the multi-tank systems, again, well, there are fixed recipes, but in this case, the recipes are based on concentrations of all the nutrients. And these concentrations may be constant during the crop, or they may be variations during the crop, depending on phenological development. As with the simple fertilizer tanks, the adjustments are made to these recipes in relation to crop appearance, weather conditions, etc. This is an example, or examples of recipes, of a recipe in which a standard solution is used for an entire crop. These are recipes for tomato, cucumber, pepper, and watermelon. We can see there are some differences in the concentrations used for different crops. For example, if we look at nitrate, tomato is 11 throughout the crop. Cucumber, which has a big demand, is 13. Pepper 12, and watermelon 11. Okay, this is an example of a standard nutrient solution for tomato in Almeria. In this case, there are variations during the crop for different phenological phases. In this case, initially 8 millimoles was applied of nitrate. Then as the crop developed, 11 millimoles. When there was a big demand for fruit growth, 14 millimoles, which was maintained until the rest of the crop. Now, briefly to discuss substrate-grown crops. Currently, it's approximately 10% of the surface area of crops. Nearly all the substrate-grown crops in Almeria are free draining. That is, the drainage is not collected and recirculated. Generally, irrigation is automatically controlled with a demand tray system, which we can see here. Time doesn't permit me to go into that, but later on, Whitehoe can answer any questions on how it works. Salinity is a very important issue and becoming a very important issue in Almeria. The drainage fractions can vary considerably between 15 and up to 40%. And generally, growers will also collect drainage from one or several bags of substrate, and they'll measure the conductivity on the farm with a portable conductivity meter. That's an important parameter in the control of substrate-grown crops. Okay, this is a quote in Spanish. The Spanish readers can actually read this. This came from the same chapter by Cadenas, Gonzalez, and Hernandez. It's, for me, a very useful observation about the different recipes that are used in Almeria. Basically, what they say is the recipes used vary appreciably, and they can be contradictory. There's a wide range of fertilizer practices in the same zone, on the same soil, and for the same crop. But the production is always very similar despite these differences. So this suggests that the nutrient supply is generally not limiting. Whatever people do, it is not really affecting the production. So why is the nutrient supply not limiting crop production? And what are the consequences? What are the consequences of the fact that variable nutrient applications are being made when nutrients aren't limiting? It suggests that there is a large nutrient supply from the soil, and that's not being taken into account. This is a schematic representation of the Inarenado soil that's used in Almeria. I think about 60-70% of the crops grown in soil use this system. Very briefly, at the bottom is the original soil, the natural soil. And then above that is a layer which might be 20 to 30 centimeters thick of soil generally imported from a quarry. This is generally a loam soil. Above that, there's a layer of manure, 2 to 5 centimeters, which is quite substantial. And above that, sand, which acts as a mulch. Traditionally, large manure applications were made at greenhouse construction. And these applications correspond to between 200 and 500 cubic metres per hectare, which means they're applying more than 1,000 kilograms of nitrogen at construction. And we can see here, this is a greenhouse being built not too long ago, and you can see that there's quite a thick layer of manure, and there's the sand on top about to be spread. And additionally, the traditional practice was every 2 to 5 years or so was to apply another manure application, or periodic manure application, a practice known as retranqueo. Now it is less common. It was applied in bands, which we can see here. And in these applications, the amount of nitrogen being applied was several hundred kilograms of nitrogen per hectare. Now, considering these amounts of manure, forgot to mention this. Commonly now, people are using products, these kind of liquid products to add organic matter. I think fulvic acids and other type of things. So the tendency for people to add organic matter through the fertigation system with these things that come out of bottles. I have no idea whether they work or not. But regarding the manure, now that Almeria, or much of the greenhouse growing areas in Almeria, are declared nitrate vulnerable zones, we need to take into account that the limit on the amount of manure nitrogen applied in 1 year can only be 170 kilograms of nitrogen. So these amounts are quite substantial, or they were quite substantial. So what are the consequences of traditional nutrient and irrigation management in Almeria? And by that I'm also including manure. There are some important considerations. We've seen this before. Firstly, fertilizers and water are approximately 10% of variable cost. It's even more than in the Netherlands. But it's still relatively low. It's not a major cost. It's not seen as a major issue for the growers. And also, fertilizers and water aren't seen as life and death issues, as pathological issues might be, or even climate control issues. So it's something they do okay. There's not a lot of pressure, as they see it, to change these things. Also, in the case of Almeria, the greenhouses are very densely concentrated, so any issues of nutrient loss to the environment, etc., become very concentrated. There's like a funnel effect. And so what are the consequences? We need to consider that Almeria is firstly an economically very successful system. It's referred to as the Almeria miracle. But also in the greenhouse soils, there is an accumulation of available P and exchangeable K, because people aren't measuring what there is. They're simply adding more and more. There's also a variable and somewhat excessive irrigation. Considering that people are often irrigating blind, they do a very good job, but there's still room for some improvement, particularly with the variability. One of the consequences of over-irrigation and the very high concentration is that there's an issue of aquifer depletion. And there's an excess nitrogen supply, and the manure is an important part of the nitrogen problem. On average, the total nitrogen supply, if we consider fertilizers and nitrogen mineralized from manure, is more than twice what the crops are uptaking. We saw from Vim numbers of an excess of 600 kilograms. The numbers are quite similar here. And as a result, there's nitrate contamination of aquifers. Okay, so I think Almeria now is approaching, it's in a transition stage from a production-based system to a more sustainable system. And it has to do that because of the economic realities and the realities of being in the European Union. So what are the tools that are available in Almeria at the moment? For irrigation, there are tools to calculate crop water requirements. We saw this in Theodore's presentation. Almost the same information. There are lookup tables and the Pro program. Also, there's been a lot of work done with soil moisture sensors to help with irrigation in Almeria. Different sensors have been evaluated, but I think there's a pretty unanimous consensus. The tensiometers are the most appropriate tool, the most appropriate sensor for this system. There's been a lot of work done on when to irrigate. People have looked at different limits with electrotentiometers, and in Las Palmerias with Sisitex and other colleagues, they're developing a system for automatic irrigation with electric tensiometers. For nitrogen management, we've developed tools to calculate the nitrogen requirements. The idea is to consider what each crop needs in each greenhouse, what is available from the soil, and the fertilizer being added is seen as a supplement. What do we need to ensure there's enough for the crop? We've developed a decision support system known as VegSys to do this calculation. It's available in Windows. It works it's in English and Spanish. So I'll rapidly move on. This is an example of the output of VegSys. It does calculate the requirements of nitrogen as a concentration. So we're trying to bridge this gap to provide tools that can agronomically consider what the crop requires, but present it in terms of the concentration. And here we've looked at two different scenarios. In blue, it's a situation in which there's no soil, no mineral in from the soil, or no manure. And in this case, the average concentration in the nutrient solution calculated by the program was 9.5 millimoles. Farmer practice is generally 12 millimoles. When we had 200 kilograms in the soil, 200 kilograms of mineral in the soil at the start of the crop, and that was taken into account by the program, the average amount to be applied dropped to 4.9. So there's a lot of potential for using tools such as this to reduce the amounts that are applied. And lastly, we're looking at various methods to monitor and evaluate crop nitrogen status. We saw some of these with Theodoro, the soil solution samplers, there's SAP analysis, and there's also the proximal optical sensors, which are receiving a lot of attention in the United States, for example. How are we going for time, Miguel? Bad. Okay, well, I might just jump this. This was some work we did between the Cacamar and University, and we put packages together to compare our improved management package, looking at tools from the Cacamar and from the university, comparing with farmer practice. And I'll just very rapidly go through this. And I just ask you to focus on the results. We're able to reduce nitrogen use, reduce irrigation use, reduce nitrate leaching and drainage. And something that was very pleasing about this is we had open days and we received a lot of visitors. We actually were going to have 2, and by popular demand, we ended up having 4, and they were all very well attended. Okay? So that's it. Thank you for your attention.